In the first equation, the variable only appears in one exponent. There's only one variable, so x equals log base 10 of 25 is going to be our solution. Similarly, in the second equation, we just have one appearance of x, so we can rewrite this as log base 2 of 15 equals 5 minus 7x. Now we have a little bit of work to do. We can subtract 5 from both sides and divide by -7. And it might be a little bit nicer to write that with a +7 in the denominator, and then that's going to change the sign of the things on top as well. So I end up with 5 minus log base 2 of 15. Example 3 is an important one to think about carefully. One thing that I hope catches your eye, and if not, will after this, the plus sign here is really important to notice. So this is a very different type of equation because that plus sign means that I have two separate terms over here. And even though the bases are related, base 4 and base 2 are both powers of 2, I can't combine them in the usual way because of the plus sign. Right? But there is something particular that I can do, right? Using the fact that b to the x plus y equals b to the x times b to the y, I can rewrite that second term in the expression and get 4 to the x plus, this is going to be 2 to the first power times 2 to the 2x power. But then what's more is I can use the fact that 2 to the 2x equals 2 to the 2 raised to the x. So that actually just equals 4x. And so what I really have is 4 to the x plus 2 times 4 to the x equals 50. And so this is really just like terms. I can write this as 3 times 4 to the x equals 50. But again, I want to be kind of careful. The examples that we've seen so far, we haven't really talked about it, but we've had like one thing raised to an exponent. We haven't dealt much, we haven't seen coefficients in front. So I don't like having that 3 in front. So what I'm going to do is divide both sides by 3 and turn this into 4 to the x equals 50 over 3. And now we have that fraction, but that's fine. We can rewrite this as x equals log base 4 of 50 over 3. And as an exact value, that's a perfectly fine final answer. Now looking at example 4, we have to be careful with this one because x appears in two exponents. So we're going to use our new strategy of taking log base 10 of both sides. Again, we could use any base, but log base 10 is convenient because we can calculate with that. And so there we go. And then I can pull those exponents to the front. This becomes x times log of 5 and x plus 1 times log of 4. And then we can solve this by distributing. Log of 4 is just a number, of course. So I'm going to keep it in that log notation because it's just a little more compact than finding the decimal version. I'm sort of avoiding rounding at this point. And now I can subtract x times log of 4 from both sides. So I have x times log of 5 minus x times log of 4. And I can factor out an x from both of those. We have just this little old log of 4 on the right-hand side. So all of this is times x, so we can divide by all of that to get our final answer. So I have x equals log of 4 divided by log of 5 minus log of 4. And so this is a pretty good version for the final answer, but we could use some rules, use some of the properties to make things smaller or simpler, different. I could write this as log of 4 over log of 5/4 using the quotient rule, and then using the change of base formula, we could change it to log base 5/4 of 4, right? So the other logarithms in the problem were log base 10. If we wanted to write it in a compact single logarithm, we could change it to log base 4/5, or sorry, 5/4. Now the equation in problem 5 can be solved in a similar way. I'm going to discuss that in a separate video and emphasize a little bit some of the ways that we can check the work after finding a solution.